Patterns, arithmetic sequences. Here's an example of an arithmetic sequence: 2, 5, 8, 11 and 14. In this case, you're given the terms of the sequence and you're asked to find the formulae for Tn and Sn for this particular sequence. So we look again at the terms 2, 5, 8, and we can see that there's a common difference between them of 3. 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3, 11, and so on. So in terms of observations, our first term, T1, also called A, is 2. We're given that value. And the common difference, D, between each two neighbouring terms is identified as 3. So we have A and D, both known. A is 2, D is 3, and we can work out the equations from that. Using the equation in the tables for Tn, the nth term is defined as A plus n minus 1 times D. But in this case we have values for A and D. So substituting those values, we get A, we have 2, plus n minus 1 times D, and D is 3. So Tn for this sequence is 2 plus n minus 1 times 3. Or 2 plus, multiplying in, 3n minus 3. Grouping the 2 and the minus 3, we get minus 1. The 3n comes down. So the nth term of this particular sequence is 3n minus 1. We can check to show that that's correct using the equation we got, 3n minus 1. When n is 1, we get 3 times 1 minus 1, or 3 minus 1, or a value of 2 for the first term. When n is 2, we get 3 times 2 minus 1, or 6 minus 1, or 5. And in the third term we get 3 times 3 minus 1, or 9 minus 1, equals 8. So our first three terms will be 2, 5 and 8. And they are the terms we had in the original question. 2, 5 and 8 as the first three terms. We now check the general expression for Sn, the sum of the first n terms. This is given in the tables as Sn is n over 2 into 2a plus n minus 1d. So we have that from the tables. But in this particular sequence, we know that a is 2 and d is 3. So we can use those values in this expression. So substituting in, we get Sn is n over 2, 2 times a, but a is 2, n minus 1 times d, but d is 3. So multiplying in now with algebra, 2 times 2 we get 4, and 3 into n minus 1 becomes 3n minus 3. Resolving this within the brackets, 4 minus 3 gives us plus 1, and the 3n follows down. So Sn, the sum of n terms for this sequence, is n over 2 into 3n plus 1. Or if we wish to multiply in, we could express it as 3n squared plus n over 2. Once again, we could check to see if it's correct. Sn is 3n squared plus n over 2, and substitute in the values for the first sum of the first term, the sum of the first two, or the sum of the first three. So when n is 1, we would get 1 squared plus 1 over 2. So 3 times 1, which would be 3 plus 1 over 2, or 4 over 2, or total of 2. In the case of the sum of the first two terms, we would say 2 squared plus 2 over 2, or 12 plus 2 over 2, 14 over 2, or 7. And taking the sum of the first three terms, we would get 3 squared plus 3 over 2, or 27 plus 3 over 2, 30 over 2, or 15. So our numbers now are 2, 7, and 15, representing the sum of the first term, the sum of the first two, and the sum of the first three. And that's what we had in our original sequence. The first term, or the sum of the first term, is 2. The sum of the first two would be 2 plus 5, which would give us 7. And the sum of the first three would be 2 plus 5 plus 8, or 15. Exactly as we got. So those equations work, and we've identified the general term Sn and Tn and how they are specifically applied in this sequence. Example 2. In this case, you're given the first term and the common difference and told it's arithmetic. So this is a standard format of the question. T1, first term, A, is equal to 5. D, the common difference, is equal to 10. We can write those two numbers here because we'll probably be using them again. A is 5 and D is 10. For example, if we were to use that in the general formula for the nth term, the nth term is given in the tables as A plus n minus 1 times D. We would get Tn in this situation would be A would be 5, and n minus 1 times D, D would be 10. So 5 plus 10 minus 10 multiplying in. And the 10n would come down, 5 minus 10 would give us minus 5. So the nth term for this specific sequence would be 10n minus 5. So once we have A and D for an arithmetic sequence, we can solve any of the questions. Here's a slight variation on the question. You're given the first two terms of an arithmetic sequence, but you're told it's arithmetic. So T1 is A is 5 and T2 is 15. Remember, you're told it's arithmetic. Given that it's arithmetic, there's a common difference between the second term and the first term. So D can be found from T2 minus T1. We know T2 to be 15. We know T1 to be 5. So 15 minus 5 is 10. D is now 10. So we now know the value of A, the first term, D, the value of the common difference, and we can solve any questions we wish with that. Example 4, a slight variation. Here you're given any two terms and told it's arithmetic. So for example, you're told that the first term, A, is 5, and the sixth term is 15, but you are told it's arithmetic. So going back to basics, we say the first term is A, the second term is A plus a common difference, the third term is A plus a common difference plus another one, T4 is A plus D plus D plus D, etc. All the way to T6, which is A plus D plus D plus D plus D plus D. More simply, we would say the first term is A, the second term is A plus a common difference, the third is A plus 2 common differences, all the way down to T6 is A plus 5 common differences. Now, with the following workings, we know the general formula, Tn, is A plus n minus 1 times D. So the sixth term would be A plus 6 minus 1 D, or A plus 5 differences, as we had before, and we're told that that's equal to 15 in this question. T1, the first term, is A plus 1 minus 1D, or 0D, or simply A. We're also told that that's 5. So with T1 equal to 5 and T6 equal to 15, we can now solve for D. For example, T6 was given as A plus 5D, and T1 given as just A. So A plus 5D minus A is 5D. From a numbers point of view, T6 minus T1 is 15 minus 5, and that's equal to 10. So joining the two, we find that 5D must equal 10. Dividing by 5 on both sides, we get D is equal to 2. And knowing that A is 5, which we know from here, and D is 2 from here, we can solve any questions with regard to arithmetic sequences. We now look at example 5, where we're using equations for Tn. You're told the value for Tn for your sequence. So, given an expression for the general term Tn, and told that in this sequence it's 4n minus 3, find the individual terms. So let's say we look at terms T1, T2 and T3. We just simply have to substitute 1 for the value of n. So T1 will be 4 times, not n, but 4 times 1 minus 3, or 4 minus 3 equals 1. T2 would be 4 times 2 minus 3, or 8 minus 3 equals 5. And T3 would be 4 times 3 minus 3, or 12 minus 3 equals 9. So our first three terms would be 1, 5 and 9. And with that we can calculate the common differences, the starting term, and proceed as before. Example 6. Given an equation for the general term Tn is 4n minus 3, find the number of terms in the sequence with values below 200. So if the sequence started with 1 and then 5 and then 9, how many of those would be below 200? Well, we can't always write them all out. So one way of doing it is to say Tn is 4n minus 3 and set it equal to 200 to find the value for n. So if 4n minus 3 is 200, 4n would be 203, taking the 3 across. Or n would be 50.75. But 50.75 makes no sense. It's either the 50th term or the 51st. We don't have the term and a half or the term and a quarter. N must be an integer. So if n is an integer or a whole number, well then we might use the number 50, rounding down or truncating, because we want the number to be below 200. Checking now, we can say T of 50 is 4 times 50 minus 3, or 200 minus 3, or 197. Whereas T51 would be 4 times 51 minus 3, or 204 minus 3, or 201. So T50, 197, T51, 201. Using the formula before, that Tn was 4n minus 3. So it's clear that there are 50 terms in the sequence with values lower than 200. We now look at example 7. Given an expression for Sn, where Sn is n squared, find an expression for Tn. This is an important form of question because it does come up and it's not in the tables. There is a relationship between Sn and Tn. For example, the first term is also the sum of the first term. And the second term can be got by adding the first two terms and taking away the sum of the first one term. In fact, Tn, the nth term, can be got from the sum of the first n terms minus the sum of all the terms up to the one before the nth term. And that relationship is an important one to remember because it's not in the tables and it is asked. Or not asked, but used. So find the value now for Sn minus 1. We were told Sn was n squared. We're now going to find Sn minus 1 because that will lead us to Tn. So substituting n minus 1 into n, we get n minus 1, where n was, squared, or n minus 1 by n minus 1. And multiplying that out, we get n by n is n squared, n by minus 1 and n by minus 1 gives us minus 2n, and minus 1 by minus 1 gives us plus 1. So the general expression now for Tn is Sn minus Sn minus 1, or n squared as we were given, minus the value we've just calculated for Sn minus 1, n squared minus 2n plus 1. So multiplying the minus into the brackets, we get n squared minus n squared. Minus by minus makes that a plus 2n, and minus by plus makes it a minus 1. The two n squareds cancel. We're left with 2n minus 1 for Tn. We can check, if we wish, finding the values for the initial terms for Tn, knowing that the value is 2n minus 1. So substituting an n value of 1, we'd get 2 times 1 minus 1, or 1. T2 would be 2 times 2 minus 1, or 4 minus 1 would be 3. And T3 would be 2 times 3 minus 1, or 6 minus 1 would be 5. So our first three terms would be 1, 3, and 5. Calculating S values from that, well, the first term would be 1. The second term would be 1 and then 3. First one would be 1 and then 3. So the sum of the first two would be 1 plus 3 equals 4. And the third term was 5, so T1, T2 plus T3 was 1 plus 3 plus 5. S3 turned out to be 9. And from our observations we can see that S1 is 1 or 1 squared, S2 is 4 or 2 squared, S3 is 9 or 3 squared. In effect, Sn is n squared, as we were given. So all our calculations have been correct. We now look at example 8, proving that a sequence is arithmetic. We're asked to prove that the sequence 1, 5, 9, 13, 17, 21 is arithmetic. This is not a straightforward question. The word prove is a very heavy burden. We have to prove that it's not just true for some cases, but for all. It has to be true for the nth term. So the general proof that a sequence is arithmetic requires Tn minus 1 to be the same, d, for all values of n. In other words, it can't just be the difference between the second and the first term, or the fifth and the fourth, or the 21st and the 20th, but the nth term minus the one before it must give the same answer every time. So let's look at the sequence 1, 5, 9, 13, 17. We know that the first term, T1, A, is 1, and we can see that the common difference starting off at least is 4, 1 plus 4 is 5, 5 plus 4 is 9, etc. So we know that A is 1 and D is 4. To find the general term, we find that Tn is A plus n minus 1d, or 1 plus n minus 1, 4, if we substitute the values of A and D. 4n minus 4 plus the 1, we get 4n minus 3. So our general formula now is 4n minus 3 for Tn. To get Tn minus 1, we substitute n minus 1 wherever there was an n. So Tn minus 1, 4 into n minus 1 minus 3. That's 4n minus 4 minus 3. The 4n is there, and minus 4 minus 3 gives us minus 7. If we subtract Tn from Tn minus 1, we get 4n minus 3 for this, 4n minus 7 for the second. And 4n minus 4n cancel, and minus 3 minus minus 7, that turns out to be a plus 7, minus 3 plus 7 gives us 4. Now, that might not seem a very important equation, but there's a lot going on there. What we're saying is that for every single possible nth term, if you subtract the term before it from it, you will get a value of 4, which is not a variable, it never changes, it's a constant, it's a common difference, therefore the sequence is arithmetic. So as the difference between Tn and Tn minus 1 is a constant and not dependent on n, it represents a common difference d. Therefore the sequence has been proven to be arithmetic. So once that wasn't a variable, you were home and dry. Example 9. Here's an example where they use algebra in addition to your arithmetic sequence. An arithmetic sequence is the following first three values: k minus 1, 2k, and 4k minus 2. And you're asked to solve for k. There's an important hint in the question. You're told it's an arithmetic sequence. So given that's an arithmetic sequence, it must have a common difference. So the difference between the first and the second term must be the same as the difference between the second and the third. So T2 minus T1 must equal the common difference, and T3 minus T2 must equal the same common difference. So given that the first term is k minus 1, the second term is 2k, and the third term is 4k minus 2, we can use that data in our equation. T2 minus T1 must equal T3 minus T2 because it's the common difference. T2 minus T1 is 2k, substituting the value, minus T1, k minus 1 in brackets, equals T3, 4k minus 2, minus T2, the minus the 2k. So 2k minus k gives us k, and the minus by minus gives us the plus 1 on the left hand side, and on the right hand side 4k minus 2k is 2k with the minus 2 remaining. So we now have an equation just in k that says k plus 1 is 2k minus 2. And if we solve the algebraic expression, we get, taking the 2k to the other side, we get k minus 2k, and taking the 1 to the other side is minus 2 minus 1. Or minus k is minus 3, or multiply both sides by minus, k is 3. So just checking our answer, if k is 3, t1 is k minus 1, or 3 minus 1, which is 2, because we had the value there. t2 we knew was 2k, and 2 times 3, because k is 3, gives us 6, and t3 is 4k minus 2, but k is 3, so 4 times 3 minus 2 is 12 minus 2 is 10. So our numbers now are 2, 6, and 10. And note that 2, 6, and 10 represent 3 consecutive terms of an arithmetic sequence, because 2 plus 4 gives us 6, 6 plus 4 gives us 10.